Today's webinar is on how to use Coreform Cubit and Python scripting to perform a refinement study, and we'll be using the openCFS solver to do that study. So again, I'm your host, Matt Cederberg, CEO of Coreform. We've got Klaus Ropert from TU Graz, who will be doing the presentation today. And so with the agenda, again, we'll be first introducing you briefly to Coreform Cubit. Then Klaus will give you an introduction to openCFS. The majority of the webinar will be a demo. We'll also be showing how to perform a refinement study with Qubit, Python, and openCFS, and then we'll have time for Q&A at the end. So the learning objectives, first of all, to again learn how to use Python scripting with Coreform Cubit to run a refinement study. So Python is one of the most powerful parts of Qubit. We'll often see new users start to use Qubit using all of the GUI and then switch over fairly rapidly to Python to use its power. And Klaus actually, ahead of the webinar, was kind enough to give us all of his journal files and Python scripts and even the slides that he'll be using. You can grab those at forum.coreform.com. Second learning objective is for you to learn about openCFS, which is an open source solver. It comes out of Central Europe that leverages Coreform Cubit for pre-processing. And then finally, I'm just grateful that Klaus is taking his time today to speak to us, and his motivation for presenting to us is to invite any new users and developers who would like to join the openCFS community. So as you learn more about that today, now you have a point of contact in Klaus, and Herman, who is supporting us as well, helps support that commercially. So if this is something of interest to you, you can get in touch with them. So if you're not familiar with Coreform Cubit, it's software that's used across industries for advanced meshing for challenging simulations. Coreform acquired this software a few years ago. It's been developed for the last few decades, co-developed with Sandia National Labs. We acquired it because we believe it's the best hex meshing software around, and we're transforming this into a preprocessor, especially for our Coreform IGA solver that we're developing. But with all these enhancements, we're also very eager to support all sorts of third-party and open source solvers. There's several dozen of them that leverage Coreform Cubit. openCFS is one of those. So it's great for CAD cleanup and import, semi-automated hex meshing, gives you a lot of control over all your mesh properties. And we've now added some IGA pre-processing capabilities there. And if isogeometric analysis is something of interest to you, you can watch some of our other webinars or get in touch with us. But today, the main thing we'll be focused on is the Python and scripting. So that's what Klaus will be sharing with you. So with that, let me turn the time over to Klaus. And Klaus Ropert is an instructor at TU Vienna. He's been teaching Coreform Cubit and openCFS for several years there. And he'll be introducing more of his research group and the interesting things that they've been doing with the first few slides. So I guess final note, this webinar is being recorded. Throughout the webinar, as you have questions, type them over chat or Q&A, and we'll either answer them back in the back channel or interrupt Klaus. So go ahead, Klaus.
All right, thanks, Matt, for the introduction. I hope you can see my screen.
Yes,
Okay, perfect. So also a warm welcome from my side. My name is Klaus Ropert, and today I want to start with first introducing the institute I'm working in, and then proceed with giving you a brief introduction into our software, openCFS, and then I'll show you a recent research project that we were working on, and then the main part, as Matt already mentioned, will be the live demonstration example. Okay, so I'm a part of the Institute of Fundamentals and Theory in Electrical Engineering here at Technical University in Graz in Austria. And our institute was founded in 1950, and our current head is Professor Manfred Kaltenbacher, and he's the head of our 4 research groups, so the high frequency group, air acoustics group, optimization and inverse problems group, and my group, the multiphysical modeling and simulation, which I will now briefly introduce. So we're mainly concerned in my research group, we're mainly concerned with three types of topics or research fields. So first of all, the electromagnetic material modeling, where we currently conducting research into some efficient vector hysteresis models, then the computational electromagnetics, where we're developing formulations for electromagnetic field problems, mainly for low frequency approximations. And then we're also implementing all the models and formulations into our software openCFS that I will introduce on the next slide, where we also conduct some research into some numerical techniques like algebraic multigrid, solver or preconditioner, and yeah, non-conforming interfaces that we'll show you in the case study. Okay, so our software, openCFS, was originally funded, started as a project called Kappa in 1985. It was then joined by Professor Kaltenbacher, and together with his PhD students, he continuously developed the software, and mainly towards coupled field problems. So that's also the reason why it was renamed to CFS++, so coupled field simulations written in C++. And last year, we launched openCFS, which is the open source version of the software, and it's licensed under the MIT license. And we're currently three, say, development headquarters. So 2 in Austria, 1 in Germany, TU Graz, TU Vienna in Wien, and Germany at the University Erlangen-Nuremberg. And if you're interested in our software, you can check out our homepage. And also we're developing on gitlab.com. So you can also have a look at our source code. And since last year, we also introduced user documentation that is still, I would say, a bit work in progress. And especially for commercial users, this is the company of Hermann Landes. So you can also have a look at this company. Okay, so every coupled field simulation software also needs to deal with single field problems. And we're currently having these 6 single field problems here in blue: acoustics, electrostatics, mechanics, magnetics, thermal, and piezoelectric simulations, whereas piezoelectric can also be considered kind of a coupled problem. And then we're having the following couplings, which is just a short excerpt actually of all the possibilities in which we can couple the different PDEs together. A recent one maybe to mention here is the magnetic thermal coupling that is not written here, so that we can also simulate induction heating processes. And what makes our software, let's say, standing out of the crowd are the analysis types. So we can handle the different this classic 3 analysis types: so static, transient and time domain, and harmonic analysis and frequency domain. But also, since this harmonic analysis is inherently linear, if you have any nonlinear problems, so for example, a solution-dependent material parameter, for example, you can use the so-called multi-harmonic analysis. And by that, you can also simulate nonlinear problems in frequency domain. And we also have some eigenfrequency capabilities, mainly used in mechanics simulation. And then a short excerpt again of some features that we're implementing in openCFS. So first of all, the non-conforming interfaces that we'll show you in the case study. We have some basic model order reduction techniques implemented, and then a big part of our German university partner is the structural optimization, where they're conducting research in topology optimization using the SIMP algorithm. Yeah, openCFS, as Matt already said, is a finite element solver. So we need an input, we need a mesh we can work on. So we can read different mesh formats like CDB, Gmesh, Nsight, GMV, and our native HDF5 format. But most of the time I'm using Coreform Cubit, and I'm especially for teaching purposes that I will show you in the demonstration example. And the results are exported as H5 format, and we can visualize it later on in ParaView, but we'll also see this in the demonstration. Okay, now some words about a recent research project that we were working on. So we were implementing non-conforming interfaces, And for those of you who are not familiar with that, there might be some physics where you have some localized solution agglomerations, especially when dealing with, let's say, wave propagation. So let's assume we're simulating an acoustic problem, and we're having a source region with acoustic sources that needs to be refined very fine, and a propagation region where we don't need such a fine mesh resolution. So you could either mesh everything with the fine mesh, which results in unnecessary many degrees of freedom. You could introduce some transition elements where you might run into troubles of ill conditioning and increasing condition number of the system. Or the approach we're using is to simply, let's say, glue the meshes together mathematically via the non-conforming interfaces. And a neat thing about that strategy is that you can also couple different element types across this interface. For example, hex with tet mesh, unstructured tet mesh, without the need for pyramid elements. And the approach we're using is the so-called Nietzsche approach, which is basically a discontinuous Galerkin method only on the interface. And by doing that, we can also introduce emotion along the non-conforming interface. And I've prepared a short video for that I can show you of an eddy current problem that was simulated. So the mesh was prepared in Coreform Cubit using aprepo commands to automatically perform these many web cuts. And basically, it's a gear wheel sensor. So you have a permanent magnet located here at the top and a conducting material that is rotating this gear wheel. And we were performing an eddy current simulation. So what you see here is the magnetic flux density. And in the conducting material, you see skin effects. And you can also see that the mesh is indeed rotating across a non-conforming interface here. Now we can also see that the mesh itself is really rotating, and we can also handle quite severe jumps on in element size. Okay, let's go back to the presentation. Yeah, what are the plans for the future development in openCFS? So we're planning to implement an Exodus reader to have better data exchange capabilities, especially with Coreform Cubit. Then we're also working on a graphical user interface. And last 2 points mainly concerning me for teaching. So we're currently improving the user documentation. As I've said, it's still a little bit under construction. And we're starting a developer manual to maybe gain some new users and introduce them without and especially to lower the entry barrier of contributing to our project. Okay, then let's jump right on to the demonstration example, how I'm typically using Coreform Cubit and our software openCFS for teaching. So this is the problem that I want to simulate now. It's an artificial example, so I totally made it up. It's not a real application. So what we basically want to do is we're having a steel cylinder here that is, let's say, welded to a rigid structure at the top and at the bottom side. And around the cylinder, there's a coil, an induction coil that is excited by an alternating current. And alternating currents, they're inducing eddy currents here in this conducting region. And eddy current effect, also called skin effect, is a boundary effect. So the higher the frequency gets, the smaller this effect gets, or the narrower this effect gets. So what we want to do is to introduce a mesh refinement towards the surface here. And after we've simulated the magnetic problem, or that after we can be sure that the mesh is correct by performing a parameter study, we're solving the coupled problem. So what we want to do is solve the magnetic problem. Then via the solution of the magnetic problem, we're evaluating the so-called Joule losses, which are the dissipative losses, so the heat source for the thermal PDE. So we're solving for the temperature field in this cylinder, and then we're coupling this temperature field to the mechanical problem via thermal strains. And the way I typically tackle this kind of problem in the teaching courses, so the multi-physical simulation 1 and 2 courses in your university. I will show you this also in the demonstration example. So we'll start from the GUI, then draw the attention to the journal editor, and then use a more abstract way to call Qubit without the GUI. So we can either call it with this terminal command, or the way we will be using it, that I'll show you, is to control the meshing procedure and the refinement study via Python. Okay, for that behalf, let's move over to Qubit. So that's the geometry we want to mesh. We'll start by meshing or by creating a whole domain. So not just this quarter domain here in light blue, but we start to construct the whole geometry and then cut it in half. So let's start. So this is the GUI, and I always have the GUI and the journal editor side by side, since for me they go hand in hand, and that's the way I prefer to use it. So, and the first two commands I always paste at the beginning of the journal file are these two, reset and undo, because if I make any mistake here in the GUI, that will probably happen, I can simply rerun the journal file, and we're back at a good state. So what we want to start with is to create the air domain first. So we want to create a large rectangle, since we're simulating this in a 2D configuration. So we click on geometry, and we want to create a surface with a defined width and height. So let's say we have a width of 100 and a height of 100 as well. So basically here everything is in SI consistent units. So it would be in meters now. However, I scale it down before exporting the mesh. I scale it down by a factor of 1/1000 to have it consistent with our simulation software, to have everything in meters. Okay, let's click apply, and this is our air domain. And then I straight away proceed with copying the command. So every click or every action you perform here, you get the journal command that I paste into the journal editor. Let me save this file. Okay. So the next step, we're creating the cylinder, and we can copy this command, and because it's a rectangle again, and let's say the cylinder has a length of 50 and a height of, let's say 10. Okay, execute this command, and this is our cylinder. And we need the coils on top and at the bottom of the cylinder. So we again copy the command for the coil. So this will be our coil, the upper part at least, and it has a width of 30 and a height of 5. Now we need to move it to the correct location. So we can click here on this button here, this transform button, and we can move the surface. So the surface 3 can move in y direction by a distance of, let's say, 30. now let me first copy the command editor. And now I say this is way too far away from the cylinder, so that was a mistake. And that's a good thing about the journal file. We can simply adapt the parameter or numerical value, rerun it, and we're good. Okay, then let's copy these two commands and construct the bottom coil. So it's the same rectangle again that we move to negative y into negative y direction, and we end up with our three surfaces for the cylinder and the coil and the air domain. However, these three surfaces, they're lying inside of the air domain, and that's not what we want to have. So we want to subtract these three surfaces from the larger air surface. So we can do this by performing a Boolean operation. So we want to subtract the surfaces from the large surface, or we can already use the quite intuitive kernel commands. So we say subtract surface 2, 3, 4, or we can even say even type 2, 2, 4 from surface 1. So from the air surface, and we want to keep all the geometries. So we write this keep keyword here, and it's basically the same as clicking here on keep originals. So that's a journal command that I think is quite straightforward. Okay, so this is our final air domain with the 3 holes in it, and we can delete the first surface that we don't need anymore. We write delete surface 1, and we're good. Okay, now at this point we have to think about how we tackle the meshing of this geometry. So the way I want to mesh this problem is with a structured hexahedral mesh, or in 2D with quadrilaterals. And for that behalf, I want to use the map algorithm of Qubit. So if I click here on the mesh, the surface mesh, and define the meshing scheme, we want to use this map scheme. And the issue is that we cannot out of the box mesh this blue region, since with this map command we can only mesh 4 noded geometry, 4 noded quadrilaterals. So the coils and the surface, they could be meshed with the map algorithm right away. However, for the air domain, we need to introduce web cuts. So we need to cut up the geometry such that we end up with purely quadrilateral domains. And we do this the following way. So we click on this scissors button here and define a cut via a coordinate plane. So let's start with a vertical cut in YZ plane, and we want to cut all surfaces, and the cutting domain has an offset of, let's say, 20. Okay, first copy the command, and now we see that this cut is not right. It has a wrong offset value. So we need to correct the numerical value. We have to remember, the length of the cylinder, length of the coil, and all the dimensions to perform the web cuts in this way, which I don't really like. So I want to make life easier, and that's the reason why I'm introducing variables. And this can be done via this prepro command. So the way to introduce variables in Coreform Cubit is the following. So I add this hashtag here and the variable name, let's say air domain, and it has a numerical value of 100. And then we can replace this numerical value by the variable. This. And if we execute these 6 lines here, I would get the same as if we were using the numerical value here. So let me copy all the variables that we need from my template. So these are the variables that we will be using. And let me also replace these lines here with the lines using the variables. Like this. So there are no new commands. Nothing's new. I've just replaced the numerical values with the variables. So if we execute this, if we run this, we're back at where we left. And now regarding the webcut commands, we can use these variables to define the locations and offset values of the webcuts. So we don't need to memorize all the dimensions we were specifying. So the final result looks like this. We're ending up with purely quadrilateral domains that we can later on mesh with the map algorithm. Okay. Now, since we want to mesh only the quadra problem, we're introducing global webcuts through the X0 plane and through the Y0 plane and delete all the unnecessary domains. So we do this again with webcut. So we introduce a webcut surface all. We want to cut through all the surfaces with, let's start with a vertical cut with X plane offset 0. Okay, looks like this. And now we can get rid of all the domains, all the quadrilaterals that we don't need, and we can here use a nice feature, the extended command line specification or extended selection, the following way. So we want to delete surface all, and now we're writing the with keyword, so this specification keyword, and I want to delete all surfaces with an X coordinate smaller than 0. So X coord smaller 0. Executing this, we get this result, and then we're introducing another webcut in the Y plane, and we're deleting all surfaces with the Y coordinate smaller than 0. Okay, so we're nearly done with the geometry creation. What you always have to consider is the following. So let's unfold this surface here and neighboring surface. And if we investigate if we look here at the top curve of this surface here, it has the ID 221, and the curve of the other surface has the ID 232. So basically the curves are overlapping, and this would result in a non-conforming mesh, which openCFS could handle, but that's not what I want to show you. So what we need to do is to say merge all and imprint all. And by running these two commands, we get the following. We get an error, of course. We end up with the following. So let's open this again. So now both surfaces share the same line, and this now results in a conforming mesh later on. Okay, now we can start with the actual meshing procedure. And again, I always want to start with a delete mesh command. So if I make any mistake here, I can simply rerun the section and we're good. And now we can specify the meshing scheme. So we want to mesh all surfaces with the map scheme. Click apply scheme and copy the command. And now, as I've explained before, I want to introduce a grading of the mesh towards this surface here of the cylinder where we're expecting the eddy currents. So the mesh should get finer and finer towards this this curve here. And we do this by meshing these vertical curves here first. Let's start with the curve mesh. We're selecting the curve that we want to mesh. So basically what I forgot to say, for this example, I want to use I want to have total control over the mesh generation. So I'm using a hierarchical meshing approach. So I basically start by meshing all the curves first, and then the surfaces. And then if it was a 3D problem, then the volumes. But now let's start with this line here. And we want to change the interval count and introduce a bias. So let's say we want to have 8 intervals, and we want to have a refinement. Maybe I zoom in. We want to have a refinement towards this edge here. This is handled by this bias factor. Okay, apply size and copy the command. Now we want to do this for all the curves. So we could either look up the curve ID of every curve that we want to mesh, or we could use extended command line features again and simply say, I want to mesh all lines with a certain length and a certain y coordinate in this or via this scheme here. So let me show you the command. So this is the same command that I've used before. So we want to apply the interval of 8 increments to every line with a length of cylinder radius, which is this length here, and a y coordinate smaller than the height coordinate. So every vertical surface here in this bottom 3 surfaces. Okay, then introduce the bias factor, and what do we need to take care of? These curves might have an inconsistent orientation, so we correct the orientation of the curves and mesh them. Okay, we end up with this curve mesh here. And in the same manner, we proceed with meshing all the other curves. I'm just pasting the commands here. So the commands are totally the same as I've just shown you, but applied to all the other curves. Okay, now we have actually total control over the mesh, over the refinement here, over the bias factor. We can simply change the intervals as we want. Okay, and now we can proceed with meshing the surface. So we have already specified the scheme, the map scheme, and we can type mesh surface all, and this is the final mesh. Okay, we're done with the mesh generation, and now we need to perform one last step in order to interact with our software, openCFS. So we need to introduce blocks and node sets. So let's say this surface and this surface, we want to address these 2 surfaces in openCFS as one region, also the coil region and the air domain. because we need to assign materials and then later on also boundary conditions, for which behalf we use the node sets. Okay. That, and let's assign a block to the surfaces. So to surface 80 and 84, click apply, and that's the command. And here in the left in the model tree, we can see this block 1 consisting of these 2 surfaces. And now we want to rename this block. So block 1, name as cylinder. So we want to use a nice name for that in our simulation software. And we perform exactly the same thing for the remaining surfaces, for the coil surface, and for the air surface. Again, there's an error. Let's rerun it. And here again, we're using these extended selection commands. So now there is another error. Let me just copy the template, rerun it. Okay, we're good. So here we're again using the extended selection command. So we're adding all surfaces to the air block except the ones we've already meshed. So this is also a nice feature of this journal commands. And then we always need to impose boundary conditions, and we do this via this node set. That's the way we address curves or boundaries in openCFS. So we want to assign, let's say, start with this curve here. And again, it works the same way as for the blocks. Now, just with the node set. And again, we rename it. And let me copy the remaining commands. So this is the final node set definition for all the curves we need to address in openCFS to apply boundary conditions or interface conditions. Okay, so we're nearly done. We only need to be consistent with the PDF I've shown you. We need to rotate the whole geometry by 90 degrees and scale it down by a factor of 1000. So rotate and also scale everything down. Again, we can do this by clicking on geometry and scale with a factor of 1e minus 3, and we apply this to all surfaces. Okay, still here, and we're done. Now we can export the mesh to ANSYS CDB format, and this format we can read in openCFS. Okay, so this was the meshing procedure with a GUI and the journal file. Let's continue with simulating this problem with openCFS, and we do this here. So our software, the input of our software is XML based. So let's perform the coupled simulation. Named it to eddy heat mech. So it's the coupling of magnetic, thermal, and mechanics PD. And we can look at the result in ParaView. We always export all the node sets and blocks. And since it's a 3-way coupling, we have 3 different physical solutions. So the magnetic, thermal, and mechanical field. Let's start with the magnetic field and investigate the eddy current density. And here we see the problem. We get eddy current density, a higher eddy current density at surface, which is physical. However, I'm not sure, or no one can be sure if we refined the mesh fine enough. So the only way we can be sure that everything is correctly meshed or meshed fine enough, we need to perform a parameter study, and we want to increase the number of increments here in this cylinder region. And we do this via the Python interface. Okay, so let's start Python with a blank file. And the thing about this journal editor is that it can automatically translate all the journal commands into Python, which is basically using this Qubit package in Python that you need to import, and it's surrounding the journal commands with, or they're simply passed to the library via string commands. Okay, so we can proceed with copying all these commands to Spider or Python, and we need to load the Qubit module, of course, and we could run the meshing procedure from Python straight away. And what I want to show you now is that we can also introduce new Python variable. Let's say eddy increment is 10 or 19, and we can use this Python variable now in our command here. So this was the previous command with an interval increment of 8, and here we want to use this Python variable that I've just created. So eddy increment and name, and we can rerun it and use this variable here. And the way I want to perform this convergence study is to have all this in a for loop, and we're changing this increment here automatically in a for loop, and perform the simulation, check the magnetic energy, and check if we see the convergence behavior. Okay, for that behalf, I've already prepared a class called eddy geometry, which is basically this Qubit file from the journal editor, but already used some Python API features. So, for example, I could get the last created ID of a surface, or another neat thing is that I can you remember these lengthy webcut commands. We can write it down in a short way by using for loops, for example. Okay, and this is the main file I've prepared. So what we want to do is to change the variable eddy interval from 10 to 25 increments, pass it to the class I've just shown you. So here it's called skin interval, this variable, and this is the variable that controls our resolution of the skin effect here in this line. So we're creating the mesh, we're meshing it. So this is the perform meshing method, which is just the execution of all the other methods, just to tidy it up, and already use this Python API feature. So we get the number of elements in the mesh and return this value to the main file, and perform the simulation of the mesh with our software openCFS, and evaluate the magnetic energy automatically in a for loop. Okay, so let's run this file. It is quite fast, usually. Okay, simulation is done. And these are the exported values, so the number of elements in the mesh and the magnetic energy from openCFS. And we can see that for the magnetic energy for the last two increments, so using 25 and 20 increments, is nearly the same. So we can say with using the increment of 20 or 25, we have resolved the skin effect fine enough. And now let's have a look at the result. Again, if we see any difference, so let's go to the magnetic simulation. Observe the eddy current density, and we see a totally different picture than before. So you really see the skin effect, so that the currents are really located at the very surface of the cylinder. And the higher the frequency gets, the smaller this effect becomes, or the narrower this effect becomes. Okay, then let's move on to the thermal problem. This was the magnetic problem. We're evaluating the Joule losses, the dissipative losses, so the heat sources. And now we can look at the temperature. So this is the temperature field in the cylinder. I did not simulate the temperature field in the air and the coil domain, so we could actually uncheck these two to end up with the temperature field in the cylinder alone. And remember, we have two symmetry axes. One is here and the other one is here. Here I have defined where it's welded to the structure a Dirichlet boundary condition. So it always stays at 20 degrees centigrade and it heats up to 78 degrees centigrade. Then using this result as an input of our mechanical PDE, there's only a mechanical problem, and it results in a displacement that looks like this, which is the magnitude displayed. The displacement is a vector, so we can also warp this geometry or show the deformation of this geometry, which then looks like this. Okay, so this is the behavior we expected. So we have a rigid connection here and at the bottom. So this is the symmetry line. And here in the region where the temperature is the highest, we expect a thermal expansion. And yeah, it's what we expected. Okay, so this already brings me to the end of my demonstration example and also to my presentation. Okay, thank you very much.
Wow, so that was outstanding. I can tell that you are an experienced and a good teacher. So thank you for your thorough explanation and demonstration. We have some time for questions if there are any. You can type them in on the Q&A chat. So while they're coming in, Klaus, I'm just curious. So the way that you taught us today, is this is how you're teaching your classes? Is that right? The same methodology?
Exactly, yeah. Only in the classes I also show them how to set up the XML files for the simulation software for openCFS, which I skipped here. Here we're using it simply as a black box solver. I've just written this this small class here as a wrapper for openCFS. So it basically calls the binary file with the simulation input file, and yeah, so basically it's the same way I teach it in classes.
That's great. And I mean, you kind of showed this to us in about a half hour. I'm curious how long it takes your students to be able to successfully run simulations that they set up in Qubit and then run in openCFS. Is it days, weeks, hours? Like how long?
Well, I'm always surprised how fast they're learning. They're learning it. Yeah, I think the main thing that helps them is the connection of the GUI and the journal editor, which is great, I think, because you always get the correct commands that you can copy into the journal file. So this is basically the key part of the meshing that's usually learned really fast. And then because I don't want to spend too much time for meshing, since we're teaching multi-physical simulations and the finite element methods behind it. So I want to quickly proceed to the actual mathematics and simulating with openCFS.
That's great. So here's just a tip from Simon that he's texting in. It's drawing awareness to the Qubit scripting commands for selecting bodies at a certain position, which comes in handy if you've got unknown geometry from other sources. I'm not sure if that's something that comes into play with your classes, Klaus.
Well, I thought I was already showing this, so maybe I'll repeat that. I usually do this with these extended, I don't know how to really call it, extended selection keywords here. So with this with keyword, we can specify the geometries that meet a certain criterion, for example, here with this with y coordinate smaller than 0. So
right. Oh yeah.
This answers the question.
That's right. Here's a question from Amish. Does every problem seem to require setting up a new Python eddy class?
No, not totally not. So this was the geometry file that he was talking about. So this Python file needs to be set up if you're using new geometry. If you're just interested in different physics, you don't need to change the calling of openCFS. You just need to change the simulation input file, so the XML file for openCFS.
Question from Juan is, he asks, is this Qubit open source? So going to clarify, Qubit is not open source. Qubit's available. We co-developed Qubit with Sandia National Lab in the US. It's available for government use through Sandia. We do enhancements and then sell it commercially as Coreform Cubit. There is a free edition called Coreform Cubit Learn. We make available for non-commercial use. That's free up to 50,000 element export limit. So that way, since there are a lot of open source solvers that interface with Qubit, that gives you a full stack of free software for those that are using it for non-commercial use. But openCFS is open source. And I don't know if there's anything else you want to say about that, Klaus. I think you pointed to where that can be obtained in your slides.
Exactly. Yeah, you can check out our homepage, opencfs.org. And I've just seen another question, maybe a quick one. How do you run in parallel, and if so, where the mesh partition is done? So the parallelization in openCFS is OpenMPI, so shared memory, and so we don't need a mesh partitioning. We're having multi-threading. Okay.
Well, Klaus, thanks again for taking the time. It's obvious that you've prepared very well, not only for this, but through your teaching over the years. Thanks again for being willing to share the scripts, which again we put on our forum, forum.coreform.com. Maybe I'll just pull that up before we leave so everyone can see where this is at. And so let's go ahead and share my screen so you can see where you can get access to the work that Klaus is sharing. So here's, if you go to the Coreform website, let's navigate right to the Coreform website and go to support form. And then here's where we go. You can go to Coreform Cubit. And here's the scripts that Klaus has been kind enough to share. So go ahead and download them there. Okay. All right. Well, Klaus, thanks again for your time. Thanks everyone for coming, and we'll see you at the next webinar.